Tonight we're going to talk about what happens when a galaxy dies. And when I say dies, I don't mean an explosion. I don't mean a collision. I mean something quieter and in many ways far more unsettling than either of those things. No cataclysm, no shockwave, no single moment you could point to and say, there, that's when it happened. A galaxy dies the way a fire dies when you stop feeding it. Slowly, from the edges inward, dimming so gradually that if you weren't watching carefully, you might not notice until it was already over. That's what makes it strange. That's what makes it worth understanding. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Let's start with something familiar. Every morning the sun rises. It lights up the sky. It warms the surface of this planet. It makes everything you've ever seen or touched or known possible. The sun is a star. It burns hydrogen fuel in its core, and that process releases an enormous amount of energy. And that energy is what we call sunlight. The sun has been doing this for 4.6 billion years. It will keep doing it for roughly another 5 billion. Every star in every galaxy in the observable universe is running the same basic process. Hydrogen fuel goes in, energy comes out, and as long as that's happening, the star is alive. Now scale that up. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. Hundreds of billions of individual suns, most of them with their own planetary systems, burning through their fuel across a disk of space, roughly 100,000 light-years wide. And the Milky Way is not unusually large. There are hundreds of billions of galaxies in the observable universe, each one containing hundreds of billions of stars. The numbers stop meaning anything after a certain point. Your brain didn't evolve to hold quantities like that. But here's what most people don't realize. Roughly half of all those galaxies have already stopped forming new stars. Not destroyed, not exploded. Still there, still full of stars, still enormous, just no longer making anything new. The stars that exist inside them are living out their lifespans, burning through their fuel, and when they die, there will be nothing to replace them. No new stars being born, no new planetary systems forming, no new anything. Just the slow, steady fading of what was already there. The implications are staggering to consider. In the current observable universe alone, these quiescent galaxies vastly outnumber the ones still actively building themselves. They represent the cosmic future that awaits nearly every star-forming galaxy that exists today. Think about that for a moment. Half of all galaxies in the observable universe alone, that's hundreds of billions of galaxies that have gone quiet, that are running down, that stopped building themselves billions of years ago. And from the outside, through a telescope, many of them still look impressive, still large, still full of light. The death is invisible if you don't know what to look for. You have to know what's missing. The blue glow of young, massive stars, the warm spiral arms churning with new formation, the raw material still being converted into something new. To understand that what you're seeing is a relic, not a living system. Our own sun sits in one of those spiral arms, in one of those still living galaxies, and it exists because the Milky Way has not yet stopped. It formed 4.6 billion years ago from a cloud of gas and dust that collapsed under its own gravity. That collapse triggered nuclear fusion. A star was born. But that cloud of gas had to be there. It had to be cold enough and dense enough to collapse. Without the raw material, without the gas, there is no collapse, no fusion, no star. Without the star, there is no solar system, no Earth, know anything that matters to us personally. The gas is everything. Consider that every carbon atom in your body, every oxygen molecule in your lungs, every element heavier than helium was manufactured inside a star billions of years ago. None of that exists without the material to build those stars. And what kills a galaxy is the loss of that gas. Not all at once, in most cases, gradually. The fresh supply of cold gas that a galaxy needs to keep forming stars gets cut off, or heated, or physically stripped away or blown out entirely by forces from inside the galaxy itself. The reservoir empties. Star formation slows further. Eventually, it stops, and the galaxy that was once brilliantly alive, churning out new stars at a rate of dozens per year, goes quiet. It doesn't vanish. It doesn't collapse. It just dims over hundreds of millions of years as the existing stars age and die and nothing comes to take their place. That process, that slow suffocation, is what we're going to talk about tonight. What actually causes it, what the different mechanisms look like, how fast or slow it happens depending on which mechanism is doing the killing, why some galaxies die early and others last longer, and what it means that so many already have. Astronomers have a word for this process, a clinical, almost gentle word for something that ends the star-forming life of an entire galaxy, and that word is quenching. If you looked at a dead galaxy through a telescope, you probably wouldn't immediately know something was wrong. That's one of the strangest things about this. There's no wreckage, no scar, no obvious sign that something catastrophic has happened. You'd see a galaxy, billions of stars, an enormous structure hanging in space, and it would look at first glance more or less like any other galaxy. But look closer, and the signal is there. It's written in color. A living galaxy, one that's actively forming stars, glows with a blue-white light. A dead one is red, not a dramatic blazing red, just a deep, warm reddish glow, like an ember instead of a flame. Astronomers have a name for these objects. They call them red and dead galaxies. That phrase is more literal than it sounds. Here's what most people don't realize about starlight. Not all stars are the same color, and color is directly tied to temperature and lifespan. Massive stars burn hot and fast. They're blue-white, blindingly bright, and they live for only a few million years before they explode. Smaller stars burn cooler and slower. They glow red or orange, and they can survive for tens of billions of years or longer. When a galaxy is actively forming stars, it's constantly producing new massive blue stars to replace the ones that die. Those blue stars dominate the galaxy's overall light output. They're so luminous that they wash out the dimmer red stars underneath them. The galaxy glows blue because of them. When star formation stops, that supply of new blue stars cuts off. The existing ones are already dying. Within a few 100 million years, the last of the massive blue stars are gone. What remains are the older, cooler stars, orange giants, red dwarfs, stars that are still burning, but burning slowly. The galaxy doesn't go dark, it shifts. The light gradually tilts toward the red end of the spectrum as population after population of hotter stars vanishes without replacement. The whole thing reddens, like a fire slowly losing its hottest coals. That's the color shift astronomers see when they look at a quiescent galaxy. It's not a violent transformation, it's a slow fade. And then there's the shape. Most star-forming galaxies are spirals. They have rotating disks, sweeping arms, structure. The Milky Way is a spiral. Andromeda is a spiral. Most of the galaxies that are actively making stars tend to have that organized, rotating architecture. Dead galaxies are almost always a different shape entirely. They're ellipticals, Smooth, featureless, roughly egg-shaped blobs of stars with no visible arms, no disk, no rotation to speak of. The transformation from spiral to elliptical usually happens through mergers. When two galaxies collide and combine, the ordered rotation of their disks gets scrambled. Stars that were moving in one direction get flung into new orbits. The graceful structure gets destroyed and replaced by something that looks, frankly, like a smear. A smooth distribution of old reddish stars going nowhere in particular. So a dead galaxy tends to look like this: an elliptical shape, reddish in color, featureless, no spiral arms, no bright blue regions of active star formation. And here's what makes that strange. These galaxies are not small. They're not dim remnants. Many of them are among the most massive objects in the observable universe. Giant elliptical galaxies can contain trillions of stars. They're enormous. They're structurally intact. They just aren't making anything new. Think about what that means on a human scale. Imagine a city, millions of people, buildings, infrastructure, all of it functioning. But no children are being born, no new buildings going up. The population is just aging. The oldest residents die, and there's nothing to replace them. Decade by decade, the city gets quieter. The buildings get older. Eventually, the last generation lives out its life, and the city is empty. That's roughly what's happening in a quiescent galaxy, except on timescales that dwarf anything we can intuitively grasp. Now consider this. In the local universe, the portion of space close enough for us to observe in detail, roughly half of all galaxies are already quiescent. Half. That's not a rare exception. That's not an unusual case. Half of the galaxies you might point a telescope at have already stopped forming stars. The universe is full of these things, enormous structures of ancient starlight, slowly dimming. Our own Milky Way is still a star-forming galaxy. It makes a few new stars every year. Not many, but some. What would it look like if that stopped? If you could travel far enough outside the galaxy and look back at it in a few billion years, assuming it had gone fully quiescent, you wouldn't see the same thing we picture when we think of the Milky Way. The brilliant blue-white regions along the spiral arms, the star-forming nebulae, the massive young stars, those would be gone. The arms themselves might be less distinct. The overall color would have shifted toward orange and red. The galaxy would still be there, still massive, still holding hundreds of billions of stars, but the light would be older, quieter, the kind of light that comes from things that are finishing rather than starting. There's a specific kind of strangeness in that image that's worth sitting with for a moment. We tend to think of death as involving destruction. Something breaks, something collapses, something disappears. But a dead galaxy doesn't look destroyed. It looks like itself, just older. The stars are still orbiting. The structure is still there. From a distance, it might even appear impressive, a vast elliptical system, glowing faintly red across millions of light years. You'd have to know what you were looking at to understand what was missing. What was missing was the future. No new stars forming, no new solar systems assembling out of collapsing gas clouds, no new planets, no new possibilities being added to the inventory. Just the old ones running their course. The stars are all still there. The galaxy is still enormous, but it's aging without replacement, running down like a clock that nobody wound. To understand how a galaxy dies, you first have to understand what keeps it alive. The answer is gas. Cold gas. Not the thin, wispy stuff floating between stars, but dense molecular clouds, enormous clumps of hydrogen and helium sitting at temperatures close to absolute zero, some of them stretching hundreds of light years across. These clouds are the raw material. Everything starts there. When a region inside one of those clouds gets dense enough, gravity takes over. The cloud begins to collapse inward on itself. As it collapses, it heats up. The pressure builds. If enough mass is there, the temperature at the core climbs into the millions of degrees, and at that point, something remarkable happens. Hydrogen nuclei start fusing into helium, and a star is born. That process, from cold cloud to ignited star, is the engine that keeps a galaxy alive. No cold gas means no collapsing clouds. No collapsing clouds means no new stars. It really is that simple. Think about what a star-forming galaxy actually is at its core. It's a system that continuously converts cold gas into stars. The Milky Way is doing this right now. Every year, our galaxy produces somewhere around 1 to 3 new stars, each one assembled out of cold molecular gas in the spiral arms. Some of those clouds produce single stars. Some fragment and produce dozens or hundreds at once, lighting up an entire region of the galaxy with fresh blue-white light. That ongoing process is what makes a galaxy look alive. Those brilliant, hot young stars dominating the light, giving spiral galaxies their characteristic blue tint. Stop the gas supply, and that process stalls. The bright young stars burn out within millions of years, and nothing new arrives to replace them. Here's what most people don't realize. A galaxy doesn't just use the gas it formed with. If that were the case, most galaxies would have run out of fuel billions of years ago. The Milky Way has been forming stars for roughly 12 billion years. At the rates it's producing stars, the gas it started with would have been exhausted long before now. So where does the additional supply come from? It falls in from outside. Galaxies are continuously accreting fresh gas from the space around them, from the vast diffuse reservoir of the intergalactic medium. Gas streams inward, cools, settles into the disk, and eventually feeds new generations of star formation. Without that ongoing replenishment, even the most gas-rich galaxy would eventually starve itself out. To understand where that infalling gas comes from, you have to zoom out. A long way out. The universe isn't a uniform soup of galaxies scattered randomly through space. It has structure, and that structure is extraordinary. Galaxies are embedded in an enormous web, a vast cosmic network of filaments, sheets, and voids that spans billions of light years. Astronomers call it the cosmic web. The filaments are made of dark matter and ordinary matter both, and they act like highways, channels through which gas flows across intergalactic distances. Galaxies sit at the nodes where these filaments intersect. Gas flows along the filaments toward those nodes, funneled inward by gravity, eventually reaching the galaxy and replenishing its supply of star-forming material. This is not a small contribution. For many galaxies, particularly younger ones in the earlier universe, this filamentary accretion is the dominant way they acquire fuel. The cosmic web is essentially a delivery system. Gas produced in the diffuse intergalactic medium gets pulled toward the filaments, flows along them toward galaxy clusters and individual galaxies, and eventually arrives as fresh cold gas ready to collapse and form stars. It's a continuous process, operating over billions of years, connecting individual galaxies to the large-scale structure of the universe itself. So a living galaxy is threaded into this web. It sits at a node, pulling gas inward, converting that gas into stars, lighting up. The whole system works as long as the gas keeps coming, but that supply is not guaranteed. It can be disrupted. It can be cut off entirely. And when it is, the galaxy starts running down. It keeps forming stars for a while, burning through whatever gas remains inside it. But without replenishment, that supply shrinks with every passing generation of stars. The star formation rate drops. The massive hot stars die and aren't replaced. The galaxy gets redder, quieter, older. What's striking is that every mechanism astronomers have identified for killing a galaxy, and there are several very different ones, ultimately comes back to this same problem. Some of them heat the gas directly, making it too hot to collapse. Some physically eject gas out of the galaxy altogether. Some cut off the filamentary supply from outside, preventing fresh gas from ever arriving. Some do all three at once. The specific physics varies enormously from case to case, but the result is always the same. Cold molecular gas becomes unavailable, and the star-forming engine shuts down. Gas is not just one factor among many in the life of a galaxy. It's the single most critical resource. Lose it, and you lose everything. The star formation, the massive young stars, the light, the biological possibility of planets around those stars, all of it. Protect it, and the galaxy keeps living. Threaten it, and you are threatening the galaxy itself. Every mechanism that kills a galaxy, no matter how different the details, is ultimately doing one thing: destroying, heating, or cutting off that gas supply. At the center of almost every large galaxy in the universe, including our own Milky Way, there is a supermassive black hole. Not a small one. Not the kind of black hole that forms when a single star collapses. We're talking about objects with masses of millions or even billions of times the mass of our Sun, compressed into a region of space smaller than our solar system. The Milky Way's central black hole, called Sagittarius A-, has a mass of about 4 million suns. That's on the modest end. Some galaxies harbor black holes with masses exceeding 10 billion solar masses. And for a long time, astronomers assumed these objects just sat there at the galaxy's center, passive and contained, pulling in whatever wandered too close. Here's what most people don't realize. These black holes aren't passive at all. When material falls toward a supermassive black hole, it doesn't fall in cleanly. It forms a swirling disk of gas and dust around the black hole, an accretion disk, and as that material spirals inward, it accelerates. It heats up. The friction and magnetic forces within the disk generate temperatures in the millions of degrees. That extreme heating releases enormous amounts of energy, not just as heat but as radiation across the entire electromagnetic spectrum, from radio waves to X-rays. Some of that energy gets channeled into jets, twin beams of plasma and radiation fired outward from the black hole's poles at close to the speed of light. These jets can extend for thousands of light years in both directions. They punch out through the galaxy's gas, through its halo, and into the surrounding intergalactic medium. And as they travel, they heat everything they touch. Think about what that means for star formation. Cold gas collapses to form stars. That's the process. Gas needs to be cold enough and dense enough to fall under its own gravity, to compress, to heat at the core until fusion ignites. But gas that's been blasted by a black hole's jets is no longer cold. It's been heated to temperatures where it simply can't collapse. It becomes too turbulent, too energetic, too diffuse. The conditions that allow stars to form are destroyed. One astronomer described this relationship in a way that's hard to forget. The idea, they said, is that in star-forming galaxies, the central black hole is like a parasite that ultimately grows and kills the host. That framing is uncomfortable because it's accurate. The galaxy feeds the black hole grows, and eventually the black hole becomes powerful enough to destroy the galaxy's ability to sustain itself. There are two distinct modes through which this feedback operates, and they work differently depending on how massive the black hole has become. The first is called thermal mode feedback. This operates in black holes on the lower end of the supermassive scale, where the energy released by infalling material heats the surrounding gas gradually. The gas gets warm enough to resist gravitational collapse, but not warm enough to be physically expelled from the galaxy. Star formation slows. It doesn't stop completely, but the rate drops. The galaxy is being suppressed rather than killed outright. This thermal mode can persist for a long time, quietly damping star formation over hundreds of millions of years. The second mode is different, more violent. At higher black hole masses, somewhere around 100 million solar masses and above, the feedback shifts into what astronomers call kinetic mode. Instead of just heating the surrounding gas, the black hole's energy output begins driving massive outflows. Winds of gas moving at thousands of kilometers per second, physically ejecting material from the galaxy. Not just heating it, not just disrupting it, throwing it out entirely, pushing it beyond the galaxy's gravitational reach into intergalactic space. When the gas is gone, it's gone. The galaxy can't get it back. And without gas, there are no new stars. The scale of these outflows is hard to absorb. Astronomers have directly observed them. A galaxy roughly 2 billion years after the Big Bang was found to have fast outflows of neutral gas streaming outward at tremendous velocity, driven by its active central black hole. When astronomers measured those outflows and calculated their rate, the numbers were unambiguous. The gas was being expelled faster than the galaxy could replenish it, faster than star formation could consume it. The black hole wasn't just slowing star formation, it was measurably, observationally, shutting it down. This was not a model or a simulation. It was a galaxy being killed in real time. Caught in the act roughly 11 billion years ago, the light from that event only now reaching our telescopes. What makes this mechanism particularly striking is how the energy scales with the black hole's size. A larger black hole accretes more material. More material means more energy released. More energy means stronger jets, more powerful outflows, gas heated and ejected at higher velocities. The bigger the black hole grows, the more destructive its feedback becomes. And the black hole grows precisely because the galaxy is supplying it with gas. So you have a feedback loop. The galaxy feeds the black hole. The black hole grows more powerful. Its energy output increases. It begins destroying the gas supply. Star formation drops. The galaxy weakens. Eventually, the black hole's own feedback cuts off the gas that was feeding it. That last part is the thing that tends to stop people when they hear it. The black hole, by destroying the galaxy's gas supply, is destroying its own food source. As the gas is heated and expelled, less and less material is available to fall into the accretion disk. The accretion rate drops. The jets weaken. The black hole settles into a quieter state. It doesn't disappear. It doesn't shut off entirely. But the furious energetic phase that drove the outflows is over, because there's nothing left to power it. The galaxy is quiescent. The black hole is starving. Both of them are quiet now, for the same reason. This self-regulating quality is one of the reasons astronomers take black hole feedback so seriously as a quenching mechanism. It doesn't require any external trigger to stop. It doesn't need another galaxy to come along and strip away the gas. The black hole does it all internally, growing powerful enough to destroy the conditions that allowed it to grow in the first place, and then fading as a consequence of its own destruction. There's something almost elegant about it, a system that contains the mechanism of its own termination. The galaxy builds the thing that kills it. The thing that kills it eventually runs out of ammunition, and what's left behind is a galaxy full of aging stars. No new ones forming, slowly running down. The black hole doesn't just kill the galaxy's ability to form stars. In the end, it starves itself too. But here's what makes the black hole feedback story stranger. The black hole doesn't start killing the galaxy the moment it forms. For most of its life, a supermassive black hole just sits there. It grows slowly. It pulls in material from its surroundings. It gets more massive over time, and during that whole period, the galaxy around it keeps forming stars, keeps pulling in fresh gas, keeps doing what galaxies do. The black hole and the galaxy coexist, almost peacefully, for hundreds of millions of years. Sometimes longer. The black hole is growing, but it hasn't yet reached the point where its energy output can overwhelm the galaxy's ability to hold onto its gas. It's too small. Its jets are too weak. The outflows it produces aren't powerful enough to do serious damage. But there is a point where that changes. Astronomers have worked out an empirical relationship, meaning they found it in the data, not just in theory, between black hole mass and the suppression of star formation. Above a certain black hole mass, the outflows and jets become powerful enough to heat the surrounding gas, push it out, and prevent new gas from falling in. Below that mass, they can't. The galaxy keeps forming stars. Cross the line, and everything changes. What makes this more specific is that the threshold isn't the same for every galaxy. It depends on the galaxy's structure. Larger galaxies, ones with more stars, more mass, more volume, need a more massive black hole before quenching can begin. A smaller, lower mass galaxy can be quenched by a relatively modest black hole. A massive galaxy requires a much more powerful one before the feedback is strong enough to matter. Think about what that means. The galaxy itself sets the bar. The bigger the galaxy, the harder it is to kill. Here's where it gets more precise. It's not just about the total stellar mass of the galaxy. It's also about physical size. Two galaxies can have the same number of stars, the same total mass, but very different physical extents. One might be compact and dense. The other might be spread out across a much larger region of space. The compact galaxy quenches earlier. Its stars are packed in tightly, the gas density is higher at the center, and the black hole reaches the critical threshold at a lower overall stellar mass. The larger, more spread out galaxy has to keep building stars, keep growing its black hole, before the feedback finally becomes strong enough to shut things down. Physical size matters independently of mass. That's not obvious, and it took careful observations across large galaxy surveys to establish it. What astronomers found, when they put all of this together, is that black holes and galaxies don't just coexist, they co-evolve. The galaxy grows, the black hole grows with it, and there's a feedback relationship between them that's been operating across billions of years of cosmic history. The two are not independent. The mass of the black hole at the center of a galaxy is tightly correlated with the mass of the galaxy's central bulge. That correlation is not an accident. It's the fingerprint of this long, slow coevolutionary process. The black hole and the galaxy have been shaping each other for most of their lives, and then the threshold is crossed. When the black hole's mass reaches the critical point, something shifts dramatically. The accretion rate, the rate at which material is falling into the black hole, drops by several orders of magnitude, not gradually, sharply. The powerful kinetic feedback doesn't just slow the inflow of gas, it reverses it. Gas that was falling inward starts getting driven outward. The outflows reach velocities of thousands of kilometers per second. Material that took billions of years to accumulate in the galaxy's center gets expelled on timescales that are geologically short by comparison. And as the gas goes, so does the fuel for star formation. The molecular clouds that would have collapsed into new stars are heated, disrupted, scattered. The star formation rate falls. It doesn't taper off slowly over billions of years the way strangulation works. Once the threshold is crossed and the feedback kicks in at full power, the decline can be fast. What's left afterward is a black hole that has cut off its own food supply. The same outflows that expelled the galaxy's gas also prevent new gas from falling back in toward the center. The accretion rate stays low. The feedback eventually quiets down, Not because the black hole has changed, but because there's nothing left to drive it. The galaxy has been transformed. Star formation has collapsed. The black hole sits at the center of a system it can no longer significantly affect because the damage is already done. There is a threshold, a specific mass, and the moment the black hole crosses it, the galaxy it lives inside begins to die. One of the strangest discoveries about dying galaxies is where the death begins. When astronomers first started mapping the star formation activity inside massive elliptical galaxies, they expected to find a relatively uniform picture. Either a galaxy was forming stars, or it wasn't. What they found instead was something far more interesting. The largest ancient galaxies weren't dying all at once. They were dying from the center outward. The cores had gone dark first. Star formation had collapsed in the interior, while the outer regions were still actively building new stars. The death was spreading, slowly, like a fire burning inward from the middle of a forest rather than racing in from the edges. Here's what most people don't realize. Astronomers surveyed about 22 massive elliptical galaxies to study this pattern in detail. Most of these galaxies were comparable in size to the Milky Way or larger. What they found was consistent and striking. 3 billion years after the Big Bang, these galaxies still showed star formation activity on their outskirts. New stars were being born in the outer arms and edges, but their centers had already stopped. The cores had shut down. The inner regions had gone cold. The quenching had begun at the heart of each galaxy and hadn't yet reached the periphery. That's not what you'd expect if something external were killing these galaxies. That's what you'd expect if something inside them were doing it. Galaxy IC 2006 is a specific example astronomers have studied in this context. It's an elliptical galaxy, and observations from both the Hubble Space Telescope and the Very Large Telescope have confirmed the same inside-out pattern. The inner regions show all the hallmarks of a long-dead stellar population. Old stars, cool stars, nothing new being formed. The outskirts tell a different story. There's evidence of star formation that persisted far longer in those outer zones before eventually shutting down too. IC 2006 essentially preserved a record of the progression. It's not a snapshot of something dying uniformly. It's a time lapse of something being hollowed out, its own center consumed first, the edges following later. Think about what that image actually means. A galaxy that looks perfectly intact from the outside, still enormous, still full of stars, but its center is already dark, already finished. The light you see from the core is old light, ancient starlight from stars born billions of years earlier, slowly fading with nothing to replace it. Meanwhile, the outer disk is still producing new stars, still bright with that blue glow that signals active formation. The galaxy looks alive at its edges. It's dead at its heart. This pattern rules out certain mechanisms almost immediately. RAM pressure stripping, for instance, is a process driven by the galaxy's environment. A galaxy moves through dense gas surrounding a cluster, and that gas pressure strips away the galaxy's own gas from the outside. If RAM pressure stripping were the primary driver of quenching in these systems, you'd expect the outer regions to die first. The edges would be stripped away before the interior. That's not what the data shows. The data shows the opposite. Interior first, exterior later. That's a signature of something internal. And that internal something points directly back to the supermassive black hole. The black hole sits at the center. Its feedback, the jets and outflows that heat and expel gas, radiates outward from the core. When the black hole crosses that critical mass threshold and begins driving powerful kinetic feedback, the gas nearest to it gets disrupted first. Star formation collapses in the region closest to the source of the disturbance. Then, as the feedback continues, and the influence of the black hole propagates outward through the galaxy. The quenching front moves with it. The dead zone expands. The boundary between active and inactive star formation pushes farther and farther from the center. The galaxy hollows out gradually over hundreds of millions, sometimes billions of years. There's something almost architectural about it. The galaxy isn't being killed from the outside. It's collapsing inward from its own center. The very engine that once helped regulate the galaxy's growth has now become the source of its unraveling. And the structure of the quenching front, the way it propagates outward in a rough expanding shell, gives astronomers a way to track how far along in this process a given galaxy is. A galaxy with only a small dead core is early in the process. A galaxy with a vast quiescent interior and just a thin ring of active star formation at the outermost edges is near the end. What makes this observationally powerful is that the pattern is consistent across many different massive galaxies. It's not a quirk of one system. It appears to be a general feature of how large galaxies die. The most dense cores are where quenching initiates. Once a critical density is reached at the center, the conditions for continued gas infall break down. The gas can no longer cool efficiently. The black hole's energy output keeps it hot and turbulent. Star formation simply cannot gain a foothold there anymore. And from that point forward, the dead zone grows. You can picture it as a sphere of silence expanding outward through the galaxy at whatever pace the black hole's feedback allows. Billions of stars still burning in the outer disk, unaware in any physical sense of what's already happened in the center. The outer regions keep forming stars for millions, sometimes hundreds of millions of additional years after the core has gone completely quiet. The galaxy is killing itself from the inside, and by the time the outer edges go quiet, the center has been dark for billions of years. Not every galaxy dies quickly. The mechanisms we've talked about so far, black hole jets tearing through the interstellar medium, quenching spreading outward from a dead core, those are violent processes. They are fast, by cosmic standards at least. But there is another way a galaxy can die, and it looks nothing like that. It is slower, quieter, and in some ways it is stranger, because from the outside nothing appears to have gone wrong at all. This mechanism is called strangulation. Some astronomers call it starvation, and that second name is probably more honest about what's actually happening. The galaxy isn't being attacked. Its gas isn't being blasted away by jets or stripped out by some external force. The gas that's already inside the galaxy stays right where it is, at least for a while. What changes is the supply line. The fresh gas that would normally fall in from the intergalactic medium, the fuel that keeps star formation running across billions of years, simply stops arriving. And without that steady incoming supply, the galaxy slowly burns through what it has left and never gets more. To understand why that matters, you have to remember that galaxies don't form stars using only the gas they were born with. They are continuously accreting new material from outside. Gas flows in along the filaments of the cosmic web, cooling as it falls toward the galactic center, eventually collapsing into new stars. That inflow is not optional, it's essential. The star formation rate in a healthy galaxy depends on that ongoing delivery. Cut it off, and the galaxy is already dying, even if nobody has told it yet. Here's where the physics gets interesting. Every large galaxy sits inside a vast halo of hot gas. When cold gas from the intergalactic medium tries to fall inward toward the galaxy, it has to pass through this halo. Under certain conditions, the halo is hot enough and dense enough that incoming gas gets hit by what are called virial shocks. Basically, the infalling gas slams into the halo material at high velocity, heats up violently, and can no longer cool down fast enough to complete the journey into the galaxy. It gets stuck, heated to temperatures where it simply cannot collapse. It hangs in the halo, unavailable for star formation. The galaxy beneath it has no idea this is happening. It just notices, over time, that less gas is arriving. What follows is a gradual decline. The galaxy has some reservoir of cold gas remaining, and it keeps forming stars with that. But the rate drops. There's no catastrophic event to point to, no dramatic shutdown moment. Star formation just slowly gets harder to sustain, like a fire that nobody is feeding. The existing fuel gets used up, and there is nothing coming in to replace it. Over 1 billion years, then 2, then 3, the rate keeps falling. After roughly 4 billion years, based on what the data actually show, the galaxy has reached the point we'd call quiescent. The lights don't go out all at once. They just keep getting dimmer. The evidence for this comes from a remarkably large study. Astronomers analyzed the stellar metallicity, essentially the chemical composition of stars, across more than 26,000 galaxy spectra. Metallicity is useful here because it acts as a record of how star formation unfolded over time. A galaxy that was abruptly starved of gas at some point will have stars with a characteristic chemical signature that differs from a galaxy that was violently stripped or merger quenched. When the researchers went through all of that data, the answer that kept coming back pointed to strangulation as the dominant quenching mechanism for galaxies below about 100 billion solar masses. Not mergers, not black hole jets. Strangulation, a slow, quiet cutting of the supply line. 4 billion years is the typical timescale. Think about that for a moment. 4 billion years is roughly how old the Earth is right now. It is the entire span of complex life on this planet. And that is how long it takes for strangulation to finish a galaxy off. Not in a dramatic burst, but in a long, unhurried, almost imperceptible decline. The galaxy doesn't know it's dying. Its stars keep forming, just at lower and lower rates, and from the outside it starts to look redder, older, quieter. This is why strangulation looks so different from merger-driven quenching. A galaxy that collides with another massive galaxy can go through a violent starburst and then collapse into a quiescent state in less than 500 million years. That's a sudden shock. Strangulation is the opposite. It's not a shock at all. It's an absence, the absence of something that should have arrived and didn't. The violence is invisible because there is no violence. Strangulation tends to be the dominant mechanism for lower mass galaxies, and there's a reason for that. Less massive galaxies generally don't have the enormous central black holes needed to drive powerful kinetic feedback. They aren't massive enough to be the primary targets in major merger events. What they are, though, is susceptible to having their inflow cut off. Their halos reach a temperature and density regime where virial shocks can effectively prevent fresh gas from reaching them, and once that inflow stops, they have no backup system to compensate. They just slowly consume what they have. For billions of years, the galaxy exists on borrowed gas, slowly running out of fuel with no way to replenish it, and eventually the last stars form, and then nothing new is born again. If strangulation is a slow death from thirst, then ram pressure stripping is something more violent. A galaxy being physically robbed. Think about what it means for a galaxy to move through space. Not empty space the way we tend to picture it, but through the dense environment of a galaxy cluster. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of galaxies, all orbiting within a vast cloud of superheated gas called the intracluster medium. This gas fills the space between galaxies in the cluster. It's thin by everyday standards, but it's real. It has mass. And when a galaxy plows through it at high speed, something has to give. That something is the galaxy's own gas supply. The intracluster medium pushes back. It exerts a pressure on the galaxy, a ram pressure. And if that pressure is strong enough, it physically rips gas right out of the galaxy as it moves. Here's the analogy that makes this easier to picture. Imagine a tree moving through a storm. The wind tears the leaves away. The branches bend. The loose material goes first. The trunk stays. That's roughly what happens to a galaxy moving through a cluster. The gas, which is loosely held compared to the stars, gets stripped away by the pressure of the medium the galaxy is passing through. The stars themselves are largely unaffected. They're bound to the galaxy by gravity in a way the gas isn't, so they stay put while the gas peels off behind the galaxy like smoke from a moving fire. This is one of the most important things to understand about RAM pressure stripping. It's a hydrodynamic process. It acts on gas and almost exclusively on gas. Tidal interactions, collisions, gravitational tugs from neighboring galaxies, those affect stars too. RAM pressure stripping does not. It targets the fuel while leaving the engine block behind. The visual evidence for this process is extraordinary. Astronomers have cataloged entire populations of galaxies showing exactly what you'd expect to see if gas were being stripped away in real time. They're called jellyfish galaxies. The name fits. These galaxies have long, trailing streamers of gas extending behind them, sometimes stretching for hundreds of thousands of light years. The galaxy itself, the stellar disk, looks relatively intact, but behind it, like the tentacles of a jellyfish trailing through water, you see the stripped gas flowing outward into the cluster environment. Some of these streamers glow. The gas in them can be compressed enough to ignite star formation, which makes the stripping process visible in a way you wouldn't expect. The galaxy is losing its future while simultaneously lighting up along its own wound. That temporary burst of star formation is one of the stranger aspects of RAM pressure stripping. As the gas is pushed and compressed by the pressure of the intracluster medium, it can reach the density threshold required for stars to form. So you get new stars appearing in the stripped tails themselves, far outside the main body of the galaxy. These stars are being born in gas that has already been separated from the galaxy. They will never be part of the galaxy's main population. And once the gas is stripped away, the star formation both inside and outside the galaxy eventually collapses. The compression that briefly sparked new births is also the force that ultimately ends them. How efficiently a galaxy gets stripped depends on several things working against each other. The galaxy's own self-gravity is working to hold the gas in place. The stronger the galaxy's gravitational grip, the harder it is for ram pressure to pull the gas free. On the other side, the density of the intracluster medium matters enormously. Denser clusters strip more effectively. And then there's the relative velocity, how fast the galaxy is moving through the cluster. A faster galaxy experiences more ram pressure. The formula that governs this isn't complicated in concept. Ram pressure scales with the density of the surrounding gas multiplied by the square of the velocity. So a galaxy moving twice as fast doesn't experience twice the stripping pressure. It experiences 4 times the pressure. Speed matters a lot. A galaxy falling into a cluster for the first time, picking up velocity as it drops into the gravitational well, can hit the dense inner regions at enormous speed and lose a significant fraction of its gas in a single pass. Here's what most people don't realize about RAM pressure stripping. It doesn't only happen in the most extreme environments. The classic picture is a galaxy plowing through a massive cluster, and that's where the effect is strongest. But the same process operates in smaller galaxy groups, and even in denser regions along the cosmic filaments that connect the large-scale structure of the universe. Galaxies can begin losing gas before they ever reach a cluster. As they fall toward the cluster along a filament, they pass through progressively denser environments. The stripping starts early and compounds as they fall deeper. By the time such a galaxy reaches the cluster core, much of its gas may already be gone. Astronomers call this pre-processing. and it means the cluster environment starts killing galaxies earlier than the cluster itself suggests. What makes RAM pressure stripping distinct from strangulation is the directness of it. Strangulation cuts the supply line from the outside and waits. RAM pressure stripping reaches into the galaxy and takes what's there. One is a siege, the other is a raid. The result is the same: a galaxy slowly starved of the material it needs to make new stars. But the mechanism and the timescale are very different. RAM pressure stripping can be efficient enough to remove most of a galaxy's gas within a few 100 million years. In cluster environments, this makes it one of the fastest environmental mechanisms we know of. The galaxy moves through the cluster, bleeding gas in a long tail behind it, and eventually there is nothing left to steal. There's a faster, more violent path to galaxy death. It begins not with suffocation, but with a collision. Everything described so far: black hole feedback, strangulation, RAM pressure stripping, those are processes that work on a galaxy from within or from its environment. They're slow in most cases. They take hundreds of millions or billions of years to finish the job. But when two large galaxies collide, the timeline compresses dramatically. What might have taken 4 billion years through strangulation can be accomplished in a fraction of that time. The universe has a more efficient method, and it's spectacular and catastrophic in equal measure. Think about what a galactic merger actually involves. Two galaxies, each containing hundreds of billions of stars, approaching each other under gravity. The stars themselves almost never physically collide. The distances between individual stars are so vast that even two galaxies passing through each other are mostly empty space moving through empty space. But the gas is different. The gas clouds don't pass through each other cleanly. When two galaxies begin to merge, they're giant molecular clouds. The cold, dense regions where stars are born crash into one another. Those collisions compress the gas. They trigger condensations. Stars begin forming at an extraordinary rate, far faster than anything a normal galaxy experiences in its ordinary life. This is what astronomers call a starburst. The galaxy isn't dying yet. It's burning brighter than it ever has. Here's what most people don't realize. That burst of star formation is consuming the galaxy's gas supply at a devastating rate. A normal star-forming galaxy, like the Milky Way, converts a few solar masses of gas into stars every year. A starburst galaxy can be doing that hundreds of times faster. The fuel that might have lasted billions of years under normal conditions gets burned through in a fraction of that time. The starburst is essentially the galaxy cannibalizing its own future. Every star being born in that violent merger is gas that will never be available for the next generation. And there's a second thing happening at the same time, something even more consequential. As the two galaxies merge, the massive black holes at their centers are being dragged toward each other. Gas and dust are funneled toward the center of the forming merger remnant in enormous quantities. The black hole begins to feed. When a supermassive black hole feeds at that rate, it becomes one of the most energetic objects in the observable universe. It becomes a quasar. Quasars are almost incomprehensibly powerful. A single quasar can outshine an entire galaxy of hundreds of billions of stars. The energy comes from material spiraling into the black hole at tremendous speeds, heating to billions of degrees, radiating across every wavelength. The region immediately around the black hole glows with an intensity that puts everything else in the universe to shame. And along with that radiation come jets, narrow, focused beams of plasma and energy launched outward at near light speed. Plowing through the galaxy's gas like a pressure wave, the quasar isn't just shining. It's acting. It's physically pushing on the material around it. Those jets and outflows are what end the starburst. The remaining gas, Whatever hasn't already been burned up forming stars gets heated, disrupted. In many cases, physically expelled from the galaxy altogether. The supply is gone. The conditions for star formation collapse. The starburst ends not because the merger is over, but because the very black hole the merger created has grown powerful enough to shut everything down. The galaxy goes quiet. It enters a phase astronomers call post-starburst, and from there it moves toward quiescence. Astronomers have actually observed this process written into the fossil record of a specific galaxy, a violent galactic merger that occurred roughly 6 to 7 billion years ago left behind a remnant that is now definitively dead, a post-starburst galaxy whose star formation came to an abrupt halt. The evidence for what happened is encoded in the stars themselves. The stellar population shows an unusually uniform age distribution. A burst of stars all formed around the same time, and then nothing new afterward. That's not what a galaxy undergoing slow strangulation looks like. Strangulation produces a gradual decline. This galaxy shows a sharp cutoff, a cliff rather than a slope. Something ended the star formation suddenly. The chemical composition of the galaxy tells the same story. When astronomers analyzed the chemical signatures in that post-starburst remnant, they found patterns consistent with cold gas being violently removed rather than simply consumed. If the gas had been slowly used up, it would have had time to be enriched by multiple generations of stars and recycled back into the next round of star formation. Instead, the chemistry suggests the gas was driven out before it could complete those cycles. The collision threw it out, and the unusual structural features of the remnant, the way its stars are distributed, how concentrated its core is, all point toward a major merger rather than any gradual process. The evidence lines up in multiple independent directions, and they all point to the same event. What makes this pathway significant isn't just the speed of it. It's the mechanism. In strangulation or ram pressure stripping, the galaxy is a victim of its circumstances. Its environment cuts off its supply, and it fades. In a merger, the galaxy's own collision creates the very agent of its death. The black hole that grows during the merger, fed by the merger's gas, becomes powerful enough to expel what's left. The violence that briefly made the galaxy shine brighter than it ever had is the same violence that guarantees it can never shine that way again. Two living galaxies crash together, burn brilliantly for a few 100 million years. Then the remnant goes dark, the starburst quenched by the very black hole that the merger created. One of the ways astronomers figure out what killed a galaxy is by figuring out how fast it died. Think about what that means for a moment. When a galaxy stops forming stars, it doesn't leave a note behind explaining what happened. There's no obvious cause of death written on the surface. What remains is a collection of stars in various stages of their lives, aging quietly in the dark. But those stars carry information. The ages of the stars, the chemical compositions locked inside them, the ratios of certain elements to others, all of it forms a record of when star formation was active, when it started to slow, and when it stopped entirely. Astronomers can read that record even billions of years after the fact. It's not unlike reading growth rings in a tree. Each ring tells you something about the conditions in a particular year, whether it was wet or dry, whether the tree grew fast or barely at all. A galaxy's stellar population works the same way. A burst of star formation leaves behind a specific signature in the ages and compositions of those stars. A gradual decline leaves a different signature. A sudden collapse leaves another. And once you know how to read those signatures, you can reconstruct the timeline of a galaxy's death, even when the death happened 10 billion years ago. Here's what that tells us. Different mechanisms leave very different fingerprints. Strangulation, where a galaxy slowly burns through its remaining gas over billions of years without any fresh supply arriving. Operates on a timescale of around 4 billion years. That's a long, slow fade. Star formation declining steadily, almost imperceptibly from year to year, but adding up over cosmic time to a complete shutdown. Merger-induced quenching is far faster. Two galaxies collide, ignite a furious starburst, and then the quasar winds blow the remaining gas out entirely. That entire process, from collision to dead remnant, can unfold in less than 500 million years. And in some observed cases, the timescale is even shorter than that. Some galaxies appear to have quenched in less than 100 million years. 100 million years. That number probably sounds enormous. It's longer than the dinosaurs existed on Earth. But on cosmological timescales, it's nothing. The universe is roughly 13.8 billion years old. 100 million years is less than 1% of that. One researcher studying rapid quenching put it bluntly: whatever mechanism is responsible, it has to be fast, almost instantaneous. Instantaneous. That word, applied to 100 million years, gives you a sense of how differently time works at this scale. What does rapid quenching tell us about the mechanism? Quite a lot, actually. A galaxy that quenches in under 100 million years wasn't strangled. Strangulation takes billions of years by definition. It's a slow process. Something fast and extremely powerful had to intervene. The leading candidates are merger-driven black hole feedback events, where the supermassive black hole at the merger core grows rapidly and unleashes kinetic outflows powerful enough to strip the galaxy's gas in a geologically brief window. Fast quenching is a fingerprint that points directly toward violent, energetic mechanisms. Slow quenching points somewhere else entirely. Here's what most people don't realize. The diversity of quenching timescales observed across the galaxy population isn't a problem for our understanding. It's actually evidence that multiple mechanisms are at work simultaneously across the universe. There is no single answer to the question of how a galaxy dies. Some galaxies are strangled. Some are blown apart by their own black holes. Some are stripped by the wind of a galaxy cluster. Some are burned out by a merger and then ejected of their remaining gas by a quasar. Each of these processes operates on its own timescale. Each leaves its own fingerprint in the stars that remain afterward. The stellar populations inside a quiescent galaxy are the closest thing we have to a witness statement. Short quenching timescales tend to produce populations with very uniform stellar ages. The stars formed in a concentrated burst and then nothing more. Longer quenching timescales produce more spread out populations, with stars of many different ages reflecting a slow decline rather than a sudden stop. By measuring those distributions carefully, using spectra gathered from the light of billions of stars blended together across the face of a distant galaxy, astronomers can estimate how long the quenching took. Not perfectly, not without uncertainty, but well enough to draw real conclusions about cause. And those conclusions have genuinely changed how the field thinks about galaxy death. When astronomers first began cataloging quiescent galaxies in large numbers, the working assumption was that quenching was probably a single phenomenon driven by a single dominant mechanism. The timescale data dismantled that assumption. The range is too wide. 4 billion years at one end, 50 million years at the other. No single process can account for both. What we're seeing across the galaxy population is a collection of different deaths, happening at different speeds, driven by different causes, leaving different signatures behind. The universe is killing its galaxies through multiple means. The timescale is often the first clue that tells you which one you're looking at. A galaxy that went dark in 50 million years died very differently from one that spent 4 billion years slowly fading. Understanding that difference is the key to understanding what did the killing. In 2024, astronomers using the James Webb Space Telescope found a galaxy that shouldn't exist, not in the sense that it defies physics, but in the sense that it defies everything our best models predicted about how early in the universe a galaxy could form, grow massive, then go completely dark. The galaxy has a designation, Ruby's UDS QGZ7. It's not a name that rolls off the tongue, but what it represents is one of the most unsettling discoveries in modern astronomy. Here's what makes it so strange. We talked about quenching timescales in the last section. How a galaxy that dies in 50 million years died very differently from one that spent 4 billion years fading out. Those timescales were already difficult to explain. Ruby's UW's QGZ7 pushes everything further. This galaxy is observed just 700 million years after the Big Bang. The universe at that point was a young, chaotic place. Galaxies were still assembling. The cosmic web was still pulling itself together. Most of the galaxies we see from that era are actively forming stars at furious rates. This one had already stopped. Think about what that requires. For a galaxy to be dead at 700 million years after the Big Bang, it had to form first. It had to gather gas, collapse it into stars, build up a substantial stellar population, then somehow switch off all of that activity before we see it. The measurements show it built up more than 10 billion times the mass of our Sun in stars in under 600 million years. Then, somewhere between 50 and 100 million years before the light we're looking at left the galaxy, star formation ceased entirely. It just stopped. 10 billion solar masses in under 600 million years. For comparison, the Milky Way has been forming stars for over 10 billion years and has accumulated somewhere around 50 to 60 billion solar masses total. Ruby's UDS QGZ7 assembled a significant fraction of that in a fraction of the time, then shut down before the universe was even a tenth of its current age. That star formation rate must have been extraordinary, burning through gas at a pace that makes even the most active galaxies we observe today look slow. And the physical size of this galaxy makes it stranger still. All of that mass, 10 billion solar masses of stars, is packed into a region only about 650 light-years across. Our Milky Way spans roughly 100,000 light-years. Ruby's UDOT's QGZ7 is over 150 times smaller in diameter, yet contains a significant portion of our galaxy's stellar mass compressed into that tiny space. The density is almost incomprehensible. The cores of today's giant elliptical galaxies are among the densest stellar environments we know of. Ruby's UDOT's QGZ7 resembles one of those cores just sitting alone, billions of years before they should have formed. Here's what most people don't realize about why this discovery was even possible. Previous telescopes couldn't see it, not because the galaxy is inherently invisible, but because of how far away it is. At that distance, the light from the galaxy has been stretched by the expansion of the universe. Visible light has been redshifted so far into the infrared that optical telescopes, even Hubble, couldn't pick it up clearly. The James Webb Space Telescope was designed specifically to see in the infrared. It can detect light that no previous observatory could gather with the same sensitivity and resolution. Ruby's UDIS QGZ7 is the kind of object that existed in the data all along, waiting for an instrument capable of reading it. So what killed it that fast, that early? That's where the honest answer is. Nobody knows for certain. The mechanisms we've discussed, black hole feedback, strangulation, ram pressure stripping, are all real. All observed, all confirmed to operate in various galaxies across cosmic history. But applying them to a galaxy that quenched at 700 million years after the Big Bang strains every model we have. Black hole feedback is the leading candidate. The galaxy's extreme density suggests its central black hole could have grown very massive, very quickly. A sufficiently massive black hole in the early universe, growing rapidly from a deep reservoir of infalling gas, could in principle have released enough energy to heat and eject gas before the galaxy had any chance to continue forming stars. But here's the problem. Our models of how black holes grow in the early universe, how quickly they can reach the critical feedback threshold, don't comfortably produce the scenario we're observing. The galaxy quenched too fast, too early. Either black hole feedback in the early universe was far more efficient than our models assume, or there is something else entirely at work, a mechanism we haven't identified, a process our current understanding of galaxy physics simply doesn't account for. Some astronomers have suggested that the extreme density of the galaxy itself may be part of the answer. When gas is compressed that tightly, star formation can consume it at a rate that amounts to a kind of self-quenching. The galaxy burns through its fuel so violently that it exhausts it in a geological eye blink rather than being shut down by an external force. That's speculative. There isn't a settled consensus. The discovery of Ruby's UDS-QGZ7 has opened a question more than it has answered one. And JWST is going to keep finding objects like this. As it continues to survey the early universe in the infrared, the expectation among astronomers is that more premature quiescent galaxies will turn up. More dead galaxies from an era when the universe should have been in the thick of its star-forming prime. Each one is a new data point pressing against the edges of what current theory can explain. The galaxy is there. The data is real. Nobody fully understands how it happened, which is one of the most honest things you can say about the state of this field right now. Here's something most people don't know. Our galaxy nearly died. Not in some distant, abstract sense, not as a metaphor. The Milky Way, the galaxy you live inside right now, the one whose outer arm contains our sun and our solar system and everything you have ever seen, went through a severe quenching episode roughly 9 billion years ago. Its star formation rate collapsed. It dropped by an order of magnitude in less than 2 billion years. If that decline had continued, the Milky Way would be a red and dead elliptical today. None of us would be here to talk about it. Think about what an order of magnitude means. That's not a modest dip. That's not a slowdown. That's the difference between a factory running at full capacity and the same factory running at 10%. Stars that had been forming at a robust and sustained rate essentially stopped. The galaxy was burning through what gas it had without replacing it fast enough to keep up. The thick disk, the older, puffier, more chemically distinct layer of stars that sits above and below the thin plane of the Milky Way, formed during this earlier era of intense star formation. And then, around 10 billion years ago, that era ended. Here's what most people don't realize about how we know this. We can't travel back in time and watch the Milky Way nearly die, but we don't have to. The stars themselves remember. The chemical composition of a star is a record of the conditions that existed when it formed. Stars born in environments with lots of supernova activity, lots of exploding massive stars, carry a high ratio of alpha elements like magnesium and oxygen relative to iron. Stars born later, after that frantic early period, carry different ratios. By reading the chemistry of stars in the solar neighborhood and across the galaxy, astronomers can reconstruct the star formation history of the Milky Way the same way a geologist reads rock layers. The Apogee Survey, which stands for Apache Point Observatory Galactic Evolution Experiment, collected detailed chemical fingerprints from hundreds of thousands of stars across the galaxy. What those fingerprints revealed was striking. In less than 2 billion years, from about 10 to 8 billion years ago, the Milky Way's star formation dropped dramatically and fast. The thick disk and the thin disk aren't just names astronomers invented for organizational convenience. They are two physically and chemically distinct populations of stars, and the gap between them is a scar. The thick disk stars are older, more metal-poor in some respects, kinematically hotter, meaning they move on more disordered orbits. They formed when the galaxy was young and violent and producing stars at a tremendous rate. The thin disk, the structure we live in today, formed afterward at a lower intensity, after something interrupted the original cycle and then allowed it to resume at reduced levels. The boundary between those two populations is the boundary between near-death and recovery. What triggered the quenching? That question is still genuinely debated. Several candidates are on the table, and they aren't mutually exclusive. One possibility is gravitational interaction with satellite galaxies. The Milky Way has always had a swarm of smaller companion galaxies orbiting it. A close passage or minor merger with one of them could have disrupted the infall of cold gas from the surrounding halo, temporarily cutting off the supply line. Another candidate is the formation of the galactic bar. The Milky Way has a central bar, a rigid, elongated structure made of stars that cuts through the core of the galaxy. When the bar formed, it would have driven gas dynamics across the inner galaxy in ways that could have interrupted star formation on a wide scale. A third possibility is simply that the gas accretion from the cosmic web slowed or heated during this period, starving the galaxy of fuel without any dramatic event triggering the change. The honest answer is that we don't know exactly what caused it. What we do know is that whatever it wasn't fatal. That's the remarkable part. Most galaxies that begin quenching don't recover. They go red and dead and stay that way. The mechanisms that shut down star formation tend to be self-reinforcing. Hot gas stays hot. Black hole feedback continues operating. The supply line doesn't come back, but the Milky Way is apparently an exception, or at least a partial one. Star formation did resume. Not at the same rate as before, not with the same intensity, but gas started collapsing again. New stars started forming. Over billions of years, the thin disk assembled itself. A quieter, more settled galaxy than the chaotic thick disk era, but a living one. Why did the Milky Way pull back from the edge when so many others don't? Part of the answer may be scale. The Milky Way is a relatively ordinary spiral galaxy, not a massive giant elliptical. It may not have a black hole large enough to maintain the kind of sustained feedback that would lock in a permanent quench. Its environment is also relatively calm, not embedded in a dense galaxy cluster where ram pressure stripping or constant harassment from neighbors would have driven the death further. The conditions that almost killed it were serious, but apparently not quite sufficient to finish the job. The thin disk built up gradually over the 8 billion years that followed the near death. It is where most of the Milky Way's current star formation happens. It is where the spiral arms wind outward. It is, in a very real sense, the Milky Way's second life. A lower key existence than the thick disk era, but stable enough to keep producing stars, keep building planets, keep generating the conditions that life requires. Our sun formed in the thin disk, roughly 4.6 billion years ago, long after the near death. That means we owe our existence not just to a star, but to a galaxy that came back from the edge. When a galaxy stops forming stars, it doesn't go dark immediately. The stars that are already there keep burning. They don't know the galaxy has died. They just continue doing what stars do, fusing hydrogen in their cores, radiating light into space, living out whatever lifespan their mass assigned them at birth. What quenching actually ends is the process of replacement. New stars stop arriving. The existing ones keep going. And what happens next plays out over timescales that are almost impossible to hold in your mind. The first stars to disappear are the most spectacular ones, massive blue stars. The giants that burn at tens of thousands of degrees consume their fuel so fast that they only live for a few million years. In a living galaxy, that's fine. New ones are being born constantly to replace them. But in a quenched galaxy, when those blue giants exhaust their fuel and collapse into supernovae, nothing comes to fill the gap. Each one that dies is simply gone. Over tens of millions of years, the brilliant blue stars that once lit up the galaxy's spiral arms wink out one by one. The galaxy's color begins to shift. The blue light fades. What's left behind starts to look redder, older, quieter. Then the intermediate mass stars go. Stars like our Sun, the G-type main sequence stars that burn steadily for billions of years, begin to exhaust their cores and swell into red giants. They shed their outer layers, leave behind white dwarfs, and those white dwarfs slowly cool. Our Sun will do this in about 5 billion years. In a quenched galaxy, this process is happening everywhere at once, across billions of stars, on a rolling timescale spread over billions of years. The galaxy is full of aging stars reaching the end of their lives, swelling, shedding, cooling, dimming. There is no new generation to take their place, just the long, slow completion of what was already started. Here's what most people don't realize about this process. It is extraordinarily slow. We talk about galaxy death as though it's an event, but the aftermath stretches across trillions of years. Red dwarfs, the smallest and dimmest stars, burn their hydrogen so gently that they can live for 10 trillion years or more. That is roughly 1,000 times the current age of the universe. A quiescent galaxy is not a dark galaxy, not for an almost incomprehensibly long time. It is a galaxy full of dim red stars quietly doing their work, so faint that from a distance the whole structure looks like nothing more than a pale red smudge. But the stars are there, trillions of them, just aging. The white dwarfs are cooling too. A white dwarf, when it first forms, glows hot and bright. Over billions of years, it radiates that heat away into space and gradually fades. Eventually, in theory, a white dwarf cools to the point where it no longer emits visible light at all. Astronomers call this endpoint a black dwarf. The catch is that the universe isn't old enough for any black dwarfs to exist yet. The cooling timescale surpasses the entire duration the cosmos has accumulated to this point. So right now, every white dwarf that has ever formed is still glowing, at least a little. But in the far future of a dead galaxy, the white dwarfs will eventually go cold too, one by one, over timescales that dwarf anything we normally discuss. Think about what that galaxy looks like at that stage. No spiral arms, no star-forming regions, no bright blue giants lighting up the edges of gas clouds. Just an ancient swarm of red dwarfs burning at a fraction of the sun's brightness, and scattered among them, the cooling remnants of everything that came before. White dwarfs fading toward darkness, neutron stars spinning down. The galaxy is still there, still gravitationally bound, still a coherent structure in space, but the light it puts out is a whisper compared to what it once was. Astronomers have started using the phrase the Red Age to describe where the universe as a whole is heading. Star formation rates have been declining for about 10 billion years across the observable universe. As galaxy after galaxy quenches, as the population of massive bright stars dwindles and is not replaced, the average color of the universe is slowly shifting toward red. It's not happening fast by any human measure, but the direction is clear. The brilliant blue and white light of young stars is gradually giving way to the dim red glow of the oldest ones. The universe is aging visibly, and the color change is the evidence. What makes this strange to sit with is that the structure persists. A dead galaxy billions of years after quenching is not a ruin in the way we'd normally picture one. There's no wreckage. The gravitational scaffolding that held the galaxy together is still there. The stars are still orbiting the galactic center. From the outside, if you could somehow stand close enough, it might look almost familiar. A large collection of stars, spread across a vast region of space. You'd have to look carefully. Look at the colors. Notice the absence of the blue-white brilliance. Notice that every region you looked at was old, before you understood that nothing new had been born here for billions of years. That absence is the whole story, not destruction, but cessation. Not darkness, but a very, very slow dimming that will not be complete for a span of time exceeding all the eons the universe has so far seen. Billions of years from now, what was once a brilliant spiral will be a vast, dim cloud of ancient red dwarfs and cooling white dwarfs, too faint to see from most distances, still technically a galaxy, but a ghost of what it was. The natural question, once you understand that galaxies can be quenched, is whether that death is permanent. It seems like it should be. Once the gas is gone, once the black hole has heated and expelled everything that could have collapsed into stars, once the supply lines from the cosmic web have been cut, what is there left to work with? The galaxy has its existing stars, aging and dimming on their own timescales, nothing new being added to the mix. That sounds final, but the universe is not always cooperative with our expectations. Galaxy death turns out to be more complicated than a simple on and off switch. Astronomers have found quiescent galaxies, galaxies that by every standard measure should be dead, with unexpected patches of star formation still occurring inside them. Not at the rate of a fully active galaxy, not enough to reverse the overall decline, but the activity is there, localized, sometimes concentrated in specific regions, detectable in ultraviolet light from young hot stars that have no business existing in a supposedly dead system. Here's what most people don't realize about these observations. They suggest the boundary between living and dead is not as clean as the word quenching implies. Some galaxies that we would classify as quiescent are, in small pockets, still making stars. The most straightforward explanation for this is a merger. Not a major collision between two large galaxies, but something smaller, a satellite galaxy, a gas-rich dwarf, falling into the larger quiescent system and delivering a supply of cold gas. Cold gas is the raw material. If you can get it into a quiescent galaxy somehow, you can restart star formation, at least temporarily. The quiescent galaxy itself has no remaining reservoir to draw on, but a small infalling companion can carry enough fuel to reignite the process in isolated regions. Think about that for a moment. A galaxy that has been dark for billions of years, suddenly lit up again in patches because something small crashed into it and left its gas behind. Post-starburst galaxies complicate the picture further. These are systems that experienced a burst of intense star formation, typically triggered by a merger, and then went quiet very rapidly afterward. They're identifiable by their stellar populations. A large number of stars, all roughly the same age, formed during that single burst, now aging together in silence. Some post-starburst galaxies show signs of star formation restarting after that initial quenching. The burst happened, then it stopped, then something new began. Whether that new activity survives long-term is a different question, and that's where the tension lives. The same black hole that participated in killing the galaxy in the first place is still sitting at the center. It hasn't gone anywhere. In the most massive systems, the black hole feedback that drove the original quenching may still be capable of firing back up if new gas arrives at the center. Fresh gas falls in, the black hole begins feeding again, jets and outflows reignite. Whatever star formation had just started gets suppressed again. The galaxy gets a brief reprieve, and then goes dark a second time. Requenching is real. The black hole is not a one-time threat. It's a persistent one. In the right conditions, it can shut down a rejuvenation just as effectively as it ended the original star-forming phase. Our own galaxy is probably the most instructive case here. The Milky Way went through a severe quenching episode roughly 9 billion years ago. Star formation dropped by an order of magnitude in less than 2 billion years. By any reasonable standard, that is a galaxy in serious trouble. But it didn't stay quenched. Star formation recovered at a lower rate and eventually built the thin disk we live in today. The Sun formed in that thin disk about 4.6 billion years ago. The quenching was real, the drop was dramatic, and yet the galaxy came back. Something, whether it was the resumption of gas inflow, the settling of internal dynamics, or some combination of factors, allowed star formation to restart and sustain itself. What conditions make rejuvenation more likely? Environment matters enormously. A quiescent galaxy sitting in a dense cluster is surrounded by other galaxies and a hot intra-cluster medium that makes it very difficult for fresh, cold gas to arrive. The same mechanism that stripped the gas away in the first place, ram pressure from the surrounding medium, will strip away any new gas that tries to fall in. But a quiescent galaxy sitting in a quieter, lower-density environment has a much better chance of receiving a gas-rich merger partner without that gas being immediately destroyed. The black hole's threshold also matters. A black hole that has settled well below its feedback threshold, no longer actively accreting, poses less of an immediate threat to any new star formation that begins. It can be reactivated, but it takes time, and in that window, new stars can form. None of this means quenching is reversible in most cases. For the most massive, most fully quenched ellipticals sitting in the centers of rich galaxy clusters, the door is almost certainly closed for good. The environment is hostile. The black hole is enormous. There is no realistic source of fresh cold gas on any meaningful timescale. But the universe is large and varied enough that exceptions exist. Those exceptions matter scientifically because they reveal the edges of the processes we're trying to understand. For most galaxies that have fully quenched, the answer appears to be yes. But the universe has produced enough exceptions to keep that question genuinely open. What's happening to individual galaxies is not a random collection of isolated tragedies. It's a pattern, and it runs across the entire history of the observable universe. When you zoom out far enough, something remarkable comes into focus. The death of individual galaxies is not scattered randomly across cosmic time. It follows a curve, and that curve tells a story about where the universe has been and where it's going. Here's the basic picture. In the local universe, the galaxies closest to us, the ones we can observe in the most detail, roughly half of all galaxies have already stopped forming stars. Half. That means if you picked a galaxy at random from the nearby universe, there's about a 50-50 chance it's already dead. No new stars, no new planetary systems, just an aging population of stars, slowly burning through the rest of their lives. But that wasn't always true. Go back far enough in cosmic time, and the numbers look completely different. Astronomers can observe galaxies at different distances, and because light takes time to travel, more distant galaxies show us the universe as it was billions of years ago, at what astronomers call redshift 2, roughly 10 billion years ago. The fraction of quiescent galaxies was much, much lower. The universe back then was dominated by star-forming galaxies. Dead galaxies were relatively rare. Something has been converting living galaxies into dead ones ever since, and the process has been running continuously for billions of years. Think about what that means. The universe has been gradually building up a graveyard of galaxies. One by one, across cosmic time, galaxies have crossed whatever threshold kills them. Whether that's a black hole growing massive enough to blow out the gas, or ram pressure stripping the fuel away, or strangulation slowly cutting off the supply. Each time it happens, the quiescent fraction climbs a little higher. The ratio shifts, and that ratio tells us the universe as a whole is growing older and quieter. There's a specific point in cosmic history that astronomers call cosmic noon. It happened roughly 10 billion years ago. That was when the universe was producing stars faster than at any other time before or since. Galaxies everywhere were actively forming stars. Gas was abundant. The cosmic web was funneling fuel into galaxy after galaxy. The universe was, in a very real sense, at the height of its productivity. That peak didn't last. After cosmic noon, the overall star formation rate began to decline. Slowly at first, then more steadily. Galaxies started quenching. The gas supply started drying up. The quiescent fraction started climbing. And the cosmic star formation rate, the total amount of stellar mass being produced across the entire observable universe per year, began dropping. It has been dropping ever since. Here's where the numbers get striking. The cosmic star formation rate today is roughly 30 times lower than it was at its peak. 30 times. The universe is not simply past its most active period. It's operating at a small fraction of what it once was. For every star being born in the universe right now, 30 would have been born at cosmic noon. The factories are still running, but most of them have slowed dramatically, and many have shut down entirely. And the ones still running are not going to run forever. The gas that fuels star formation is a finite resource. Galaxies can only tap so much of it from their surrounding halos and the cosmic web before it's either consumed or heated beyond use. Some astronomers think the overall star formation rate will continue declining more or less as it has, following the same general curve toward lower and lower numbers. Others think there may be thresholds, points where the decline accelerates, but nearly everyone agrees the direction is the same. Down. Will it ever reach zero? That's the more unsettling question. The honest answer is that it almost certainly will, eventually. There will come a point, billions or trillions of years from now, when the remaining star-forming galaxies have exhausted their fuel. One by one, they'll quench. The last star-forming galaxy in the observable universe will form its last star, and then it too will go quiet. We're not close to that point, not even remotely. But the trajectory is already set, and it has been set for 10 billion years. What makes this strange to sit with is that we're inside the decline right now. The universe is not at its beginning, and it's not at its end. It's in the middle stages of a long, slow transition from a cosmos that was burning brightly to one that will eventually grow cold and dark. We happen to exist during the decline, after the peak, in a universe that is still producing stars but doing so at a fraction of its former rate. From a cosmic perspective, we live in a quieter era than the one that made many of the stars visible to us tonight. There's something worth pausing on there. The light from those stars, many of them formed near cosmic noon, when the universe was far more active than it is today, has been traveling toward us for billions of years. We're looking at the universe's past productivity every time we look up. The activity that produced much of what we see in the night sky happened in an era the universe has already left behind. The universe is not in the prime of its life. It passed that peak roughly 10 billion years ago, and we are living in its long, slow afternoon. When a galaxy dies, it often doesn't just stop making stars, it changes shape entirely. We've been talking about quenching as a process that shuts down star formation, and that's accurate. But the full picture includes something more visible, more structural. The galaxy itself gets physically transformed. A spiral galaxy, with its disk, its arms, its graceful rotating structure, can be reshaped into something almost unrecognizable. What was once a flattened, organized system becomes a featureless blob of stars moving in random directions. And the mechanism behind that transformation is collision. Here's what most people don't realize about the relationship between shape and death. They're connected, but they're not the same thing. Not every elliptical galaxy has stopped forming stars. Some ellipticals are still actively producing new ones, just at reduced rates. And some spiral galaxies have already quenched. They've stopped forming stars but kept their structure intact. The shape change and the death of star formation often travel together, but they don't have to. What links them is the merger. A major collision between two galaxies tends to do both things at once. It scrambles the structure, and it disrupts the gas supply. You get a shape transformation and a quenching event wrapped into the same catastrophe. To understand how a spiral becomes an elliptical, you have to think about what holds a spiral together in the first place. Spiral galaxies are rotating systems. The disk exists because of that rotation. Gas and stars orbit the galactic center in roughly the same plane, moving in roughly the same direction. That ordered motion is what creates the flat disk and the spiral arms. When two spirals collide, that order gets destroyed. The gravitational fields of each galaxy pull on the other. Stars that were moving in organized orbits get flung into new trajectories. The result is a system where stars are moving in every direction, scattered through 3 dimensions instead of confined to a flat plane. But the collision itself doesn't happen all at once. Think about the timescales involved. Two galaxies approaching each other for the first time are separated by hundreds of thousands of light years. They take hundreds of millions of years just to complete the first pass. As they get close, gravity stretches each one. Long tidal tails of stars and gas get pulled out into space, extending for hundreds of thousands of light years behind each galaxy. If you looked at two spirals in the early stages of a merger, you'd see distorted shapes, warped disks, these enormous streaming tails of material reaching into the dark between them. The antennae galaxies are the clearest example of this that we've ever observed. They're two spiral galaxies in the process of merging right now, located about 45 million light years away. When you look at images of them, you can see exactly what the early stages of a major collision look like. Two bright cores still visible, each one the remnant nucleus of the original galaxy. And stretching away from both of them, two long curving tails of stars shaped like insect antennae, hence the name. The tails are made of billions of stars that were pulled loose by the gravitational interaction. The antennae are tearing each other apart slowly, over hundreds of millions of years. That's what the process looks like from the outside. What's happening on the inside during all of this is where the star formation story comes in. As the two galaxies collide, the gas clouds they each contain don't just pass through each other the way the stars mostly do. Gas clouds interact. They compress against each other. They shock and heat and collapse. And that collapse triggers star formation on an enormous scale. Starbursts ignite across the merging system. In the antennae, astronomers have counted over 1,000 bright young star clusters forming in the region where the two galaxies are overlapping. The merger is creating new stars at a rate far higher than either galaxy managed on its own. But that surge doesn't last. The same violence that compresses the gas and ignites those starbursts is also funneling enormous amounts of material toward the center of the merger, toward the supermassive black holes that both galaxies brought into the collision. Those black holes eventually merge into a single, more massive one. As more gas pours in, the black hole feeds, grows, and begins driving powerful outflows. The remaining gas, what wasn't consumed in the starburst, gets heated or expelled. The starburst burns out, the fuel is gone, and the merged system goes quiet. What's left behind is the elliptical. No arms, no disk, No rotation axis that everything orbits in the same direction. Just a smooth, roughly spherical distribution of stars moving in orbits that point every which way. From the outside, it looks like a simple, featureless blob of reddish light. The more massive the original galaxies, the more massive the elliptical they produce. The largest ellipticals we know of, the giant ones sitting at the centers of galaxy clusters, almost certainly got that way through repeated mergers over cosmic time, each collision adding more mass and deepening the formlessness. The violence that creates an elliptical is also, in most cases, what finishes off the galaxy's star-forming life. The merger drives the starburst burns the gas, the black hole expels the rest. The galaxy is left with no fuel and no structure. Two living spirals collide, and what emerges is something aged and still before it even forms completely. The spiral arms are gone. The disk is gone. The graceful rotating structure that defined the galaxy for billions of years is scattered into a featureless, slowly dimming sphere. Our galaxy has a death date, and we can calculate roughly when it is. The Milky Way is still alive in the sense that matters most. It's still forming stars, but the rate at which it does that has been declining for billions of years. We're not in the prime of our galaxy's star-forming life. We're somewhere past the peak, on the long downward slope. And waiting for us, roughly 4 to 5 billion years from now, is a collision that will change everything. Andromeda is coming. Right now it sits about 2.5 million light-years away, a faint smudge in the night sky, visible to the naked eye if you know where to look. Most people don't notice it. It doesn't look threatening, but Andromeda is falling toward us at roughly 70 miles per second. It has been for a very long time. The two galaxies are locked in each other's gravity, and that distance is closing. When astronomers mapped Andromeda's motion precisely enough to measure its sideways drift, they confirmed what simulations had been suggesting for decades. This is not a near miss. This is a direct hit. Here's what most people don't realize about galaxy collisions. The stars themselves almost certainly won't crash into each other. Think about the actual scale involved. Stars are enormous objects by human standards, but the distances between them are so vast that a galaxy is mostly empty space. If you shrank the sun down to the size of a grain of sand, the nearest neighboring star would still be miles away. When the Milky Way and Andromeda pass through each other, the odds of any two stars making direct contact are essentially zero. The galaxy is too empty for that. The gas clouds are a different story. Gas fills the space between stars in broad, diffuse regions. Unlike stars, those clouds are big enough and dense enough to collide with each other when two galaxies merge. When they do, they compress, they heat, they collapse. And when gas clouds collapse fast enough and densely enough, they form stars, enormous numbers of them, in a very short period of time. This is what astronomers call a starburst. The early stages of the Milky Way-Andromeda merger will likely trigger exactly this kind of event. Burning through enormous reserves of gas in a burst of star formation unlike anything our galaxy has seen in billions of years. The night sky during this process will be something extraordinary. Right now, Andromeda occupies a patch of sky roughly 6 times wider than the full moon. But it's so faint that most of that is invisible to the naked eye. As the merger begins, hundreds of millions of years from now, that will change. Andromeda will grow. Its light will spread across a larger and larger portion of the sky. Eventually, it will be impossible to miss. A massive, distorted structure stretching across a significant fraction of the visible sky. Lit up with new star formation, laced with tidal tails of stars stretched out by gravitational forces. The night sky will look nothing like what it does today. The familiar band of the Milky Way will be disrupted. New concentrations of light will appear in new directions. If anything lives on Earth to see it, they will not recognize the sky. The collision itself unfolds over hundreds of millions of years. This is not a sudden impact. The two galaxies will pass through each other, swing back, pass through again, each pass disrupting them further, pulling out long tidal streamers of stars, scrambling the orbital structure that took billions of years to build. Eventually, the two cores will spiral toward each other and merge. The result has a name, Milkomeda, sometimes called Milkdromeda. It won't be a spiral galaxy anymore. It will be an elliptical, a massive, featureless blob of stars without the organized rotating disk structure that defines galaxies like ours today. The ordered beauty of the spiral arms will be gone, scattered by the violence of the interaction into the smooth, rounded distribution of stars that characterizes elliptical galaxies everywhere. What happens to our solar system in all of this? The honest answer is that it probably survives, just in a different place. The Sun and its planets are unlikely to be destroyed in the merger. The stars are too far apart for direct collisions. What's more likely is that the gravitational chaos of the merger reshuffles stellar orbits throughout the galaxy. The solar system ends up somewhere different in the resulting elliptical, possibly much farther from the galactic center than it is today, possibly on a completely different orbital path. Different neighborhood, same solar system. Strange to think about, the same sun, the same planets, sitting inside a galaxy that no longer resembles the one they formed in. The bigger question is, what happens to star formation? The merger will likely burn through a significant fraction of the remaining cold gas in a starburst phase. After that, the combined supermassive black holes at the centers of both galaxies, including our own Square A.I, will themselves merge into a single, far more massive black hole. And that black hole, swollen by the merger, may cross the kind of feedback threshold we talked about earlier. It may become massive enough and active enough to heat and expel whatever gas remains. If that happens, Milkomeda goes quiescent. The starburst ends, the black hole blows out the last of the fuel, and the resulting elliptical spends the rest of its existence slowly aging, its stars growing older and dimmer, with nothing new being born to replace them. That is the probable future of the Milky Way, not a quiet fading, not a slow strangulation, a collision, a final blaze of star formation. Then the lights going dim one by one over trillions of years. 4 to 5 billion years from now, the Milky Way and Andromeda will be colliding. What emerges from that collision will be something unrecognizable. A giant aging elliptical, its great star-forming days behind it. Everything we've described happening to individual galaxies is also happening to the universe as a whole, just on a longer timescale. Every galaxy that quenches, every spiral that fades into a red elliptical, every gas supply that gets cut off or ejected or heated past the point of collapse, that's not just a local event. It's part of a larger pattern. The universe has been converting star-forming galaxies into dead ones for billions of years now, and it isn't finished. What we're watching happen to individual galaxies today is a preview of what's coming for everything. The cosmic star formation rate peaked roughly 10 billion years ago. Astronomers call this period cosmic noon, a time when galaxies across the observable universe were forming stars at a rate perhaps 30 times higher than today. Since then, the rate has been falling. Not crashing, not stopping suddenly, just declining, steadily and consistently, the way a fire burns lower after the wood runs out. Today, the universe makes far fewer stars per year than it did at its peak, and that decline isn't going to reverse. The the gas supply across the cosmos is being consumed, heated, ejected. Galaxy after galaxy crosses the threshold into quiescence. The universe is doing at the largest scale exactly what we've been describing at the scale of individual galaxies, running out of fuel. Physicists who study the deep future of the universe describe it in terms of distinct eras. Right now, we live in what's called the stellar era. This is the age of stars. Galaxies are still present, still visible, still lit from within by nuclear fusion. It's what we think of when we imagine the night sky. But the stellar era won't last. Over the next few trillion years, star formation will slow to nearly nothing across the entire universe. The last new stars will form from the last pockets of cold gas still dense enough to collapse. After that, no new stars. The ones that exist will simply live out their lifespans and die. The most massive stars are already gone. They burned out within millions of years of forming. Mid-sized stars like our Sun live for billions of years, and many of those are already white dwarfs. What's left burning in the late stellar era will be almost entirely red dwarfs. Dim, cool, extraordinarily long-lived stars that can burn for trillions of years on almost nothing. They don't produce much light. A galaxy full of red dwarfs is a profoundly dimmer place than a galaxy full of stars like our Sun. The light is there, but it's faint and red and thin. Eventually, even the red dwarfs burn out, and then the universe enters what's called the degenerate era. Think about that for a moment. No stars. The galaxies, or what used to be galaxies, are now populated almost entirely by white dwarfs slowly cooling, neutron stars, and black holes. White dwarfs radiate heat into space and gradually cool over hundreds of billions of years. They don't fuse anything. They don't shine the way a star shines. They just cool slowly from white to yellow to orange to red to a dim infrared glow. Eventually, they're black dwarfs, cold, dark, inert masses of carbon and oxygen, roughly the size of Earth. There isn't a single confirmed black dwarf in the universe yet. The universe isn't old enough to have made one. But they're coming. Imagine standing on a hypothetical planet 100 billion years from now. The night sky would be nearly unrecognizable. Most of the galaxies visible to us today would be completely invisible, not because they've disappeared, but because cosmic expansion has carried them so far away that their light can no longer reach us. The galaxies still within view would be dim. The brilliant blue stars are gone. The bright yellows are gone. What remains is sparse and faint, far fewer points of light, far more darkness between them. The sky at night would be darker than anything we can observe today. The parallel to individual galaxy death is exact. What we described happening to a quenched elliptical, old stars aging without replacement, the galaxy growing dimmer as each population fades, is what the universe itself will look like, just stretched across a time scale that makes a galaxy's lifespan look brief. And after the degenerate era comes something that barely deserves a name: the dark era. Black holes slowly evaporate through a process called Hawking radiation, releasing energy so slowly that it would take longer than any human number system was designed to express. Protons may decay over time scales so vast, they make the current age of the universe look like a single heartbeat. Eventually, even the black holes are gone. What's left is almost nothing. A thin sea of particles, the last remnants of everything that ever existed, spread across a universe so large and so cold that it will never interact with itself again. Here's what's worth holding on to in all of that. The atoms don't disappear. The carbon forged in the cores of massive stars billions of years ago, the oxygen, the iron, the calcium, those atoms persist. Nuclear physics doesn't erase them. They outlast the stars that made them, the galaxies that contained them, the entire stellar era of the universe. They drift cold and dark and scattered in the vast expanding space of the late universe, no longer part of anything we'd recognize as structure. The matter that makes up the stars that exist right now will persist long after the last of them burns out, drifting cold and dark through a universe that has forgotten what light was. When you understand what quenching actually is, what it takes away and what it prevents, galaxy death stops being an abstract cosmological concept. It becomes something much closer to home. When a galaxy stops forming stars, it isn't just losing a process, it's losing every planet that would have formed around those stars, every possible ocean, every possible atmosphere, every possible chain of chemistry that might have gone somewhere interesting over 1 billion years. Quenching doesn't just end a galaxy's future, it cancels every future that galaxy was ever going to produce. Here's what most people don't realize when they think about the universe and our place in it. We exist in a specific window, not just on Earth, not just in the solar system, but in cosmic time itself. The universe had to run through several generations of stars before it could make us. The first stars were almost pure hydrogen and helium. No carbon, no oxygen, no iron, no calcium. The heavy elements we're built from had to be forged inside stars over billions of years and scattered back into space when those stars died. That took time, enormous amounts of time, and it required galaxies that were actively forming stars, dying stars, recycling their material back into the gas clouds that would form the next generation. A galaxy that quenches early takes all of that offline. The forge shuts down, but the window closes on the other side too. The cosmic star formation rate has been falling for 10 billion years. Galaxies across the observable universe are quenching one by one. The fraction that are still actively forming stars gets smaller as time goes on. We happen to exist at a moment after enough stellar generations to produce the elements we need, but before so much quenching has occurred that the conditions for planets and chemistry are gone. That window is not infinite. It has edges on both sides, and we are somewhere in the middle of it. Our own galaxy nearly closed that window 9 billion years ago. The Milky Way went through a quenching episode between 10 and 8 billion years before the present. In less than 2 billion years, its star formation rate dropped by an order of magnitude. If that drop had been permanent, the thin disk never forms. The sun never forms inside that thin disk. Nothing we know about happens. The entire chain of events that led to this planet and everything on it was contingent on a galaxy pulling back from the edge of death. Think about that for a moment. Not the sun, not the Earth, not the right chemistry in the right ocean. A galaxy. The survival of an entire galaxy is what made room for us. And we don't fully understand why the Milky Way recovered. The quenching wasn't permanent. Star formation came back at a lower level and built the thin disk over the following billions of years. Our sun formed in that disk about 4.6 billion years ago. Whatever interrupted the gas supply 9 billion years ago eventually released it, or new gas found its way in, or the conditions shifted in some way that allowed the galaxy to keep going. The details are still being worked out, but the outcome is the one we're living inside. Every mechanism we've discussed throughout this video is ultimately a mechanism for destroying the conditions that make something like us possible. Black hole feedback heats and ejects the gas that would have formed the next generation of stars. Ram pressure stripping tears that gas away as a galaxy moves through a cluster. Strangulation cuts off the supply from outside until the existing gas runs dry. Each one of these processes, when it works completely, produces a galaxy where no new planets form. No new rocky worlds with liquid water and thick atmospheres. No new chances. Just the slow fading of whatever was already there. The galaxies we call red and dead aren't empty. They're full of stars, billions of them, orbiting in the same structures they've occupied for billions of years. But they're old stars, cooling, dimming, the white dwarfs gradually losing heat, the red dwarfs burning so faint and slow they'll outlast almost everything else in the universe. None of that old light is making new planets. The heavy elements locked inside those aging stars and in whatever rocky worlds orbit them are stranded there. The forge is cold. Whatever life might have existed in those systems has whatever time it has left, and then the clock runs out with no replacement coming. When you look at a red elliptical galaxy through a telescope, that's what you're seeing. A system that used to be capable of producing new worlds and isn't anymore. It's enormous. It contains more stars than you can count. It looks impressive by any reasonable standard, but it has no future in the way that matters. No new stars, no new planets, no new chances for something to develop over the course of 1 billion years and look up and wonder where it came from. The scale of what's lost in a single quenching event is almost too large to hold in your mind. A galaxy contains hundreds of billions of stars. Each star is a candidate for a planetary system. Each planetary system is a candidate for a world with the right conditions for chemistry to do something interesting. Quenching doesn't end one of those chances. It ends all of them, every future one that galaxy ever had. Multiply that by the thousands of galaxies that are quenching across the observable universe right now, and the scale of it becomes genuinely difficult to sit with. And yet, the most immediate version of this story is the one we're already inside. A specific galaxy, an ordinary spiral in an ordinary part of the universe, came close enough to dying that it dropped to a fraction of its former star formation rate, then recovered. That recovery, over billions of years, produced the conditions for one star in one quiet arm of that galaxy to form with a rocky planet at the right distance. We exist because our galaxy survived, because the gas kept flowing, because the stars kept forming, because in one spiral arm of one ordinary galaxy the conditions held long enough for matter to arrange itself into something capable of looking up and asking why.